Hello and welcome to the latest episode of the Gradient Podcast. We interview various people who research, build, or use AI, including academics, engineers, artists, entrepreneurs, and more. I am your host, Daniel Bashir, and in this episode, I am very excited to be interviewing Professor Stuart Russell. Stuart Russell is a professor of computer science and the Smith Zeta Professor in Engineering at UC Berkeley, as well as an honorary fellow at Wadham College, Oxford. Professor Russell is the co author with Peter Norvig of the popular and universally acclaimed textbook Artificial Intelligence A Modern Approach. He is the founder and head of Berkeley's Center for Human Compatible Artificial Intelligence, and recently authored the book Human Compatible Artificial Intelligence and the Problem of Control. He has also served as co chair on the World Economic Forum's Council on AI and Robotics. This was an incredibly fun episode for me. It was fascinating to speak to somebody who's been in the field for so long. If you've followed Russell's work recently, then you've probably heard plenty about his new book, Human Compatible, that I mentioned earlier. I chose to take this interview in a rather different direction and query him about his earlier work. We went into some topics like rationality, meta-reasoning, and how he's thought about the field over time. This turned out to be a lot more like a traditional interview than a conversation because I think he just had so much to say, and I was certainly listening with rapt attention. I hope you'll enjoy his words and the topics we covered just as much as I did. And if you do find yourself interested in the topics about human compatibility that we covered just a taste of at the end, then he has plenty of other interviews, as well as his book, of course, that you can dive into for more information. Finally, if you haven't already, you should go ahead and subscribe to The Gradient on Substack. You'll get this podcast, as well as our newsletters and articles sent directly to your email. And if you've been enjoying the show, it would be wonderful if you would leave us a kind review on Apple Podcasts, Spotify, or wherever you're listening to this. And now, without further ado, Stuart Russell. Professor Russell, I expect your answer to this question is going to be fairly interesting, given that out of all the guests we have, I think you're somebody who has thought about this question of what is AI supposed to be doing? What is this field all about anyway? More so than many of the guests we've had. So, still to give you kind of the basic question we ask everyone at the beginning of these interviews, how did you get into AI?
So I would say as soon as I understood what a programmable object was, I wanted to make it intelligent. The first programmable object I got my hands on was the Cambridge Sinclair Scientific, which is a calculator that allowed you to write programs and execute them. But the programs could be a maximum of 36 keystrokes. So not even a tweet. And so it was sort of hard to write a lot of AI programs using that. And then when that was when I was 12. I think when I was 14, I started doing an A-level in computing at a college near my school. And they had a real computer, an IBM 1130. So then I started writing programs that would learn to play tic-tac-toe by themselves. So a sort of reinforcement learning thing. Bought the few AI books that existed at that time, including Nils Nilsson's book on learning and problem solving, and Bertram Raphael's Thinking Computer, and a few others. And then the following year, I got access to the giant supercomputer at Imperial College. So I would take the bus every Wednesday with all my punch cards and wrote a big chess program. So, um, so I was already quite interested. I used to read a lot of science fiction when I was young as well. So that contributed, I think. Um, but I think at that point, my professional intention was to be a theoretical physicist. And I always thought of AI as something you could do as a hobby, because it wasn't, in universities at that time in the UK, there was almost nothing happening. Um, so, but then I found out you could do a PhD in it, and eventually I switched from physics to computer science at Stanford. But it always seemed to me that those are the sort of two most important questions. How does the mind work, and how does the universe work? Yeah. It seems
Seems like
to me that most of how the universe works is already worked out. So there's more scope in the other question.
it does seem like many great minds have identified those as the two major problems: the big problem of the cosmos, and then the problem we have within our own minds. It also does seem like a lot of people transition over from the physics world to the AI world, which I find interesting, but also makes a lot of sense. There are many big problems to be solved on both sides, perhaps some parallels between the two. One thing I'd love to know is when you were first getting into AI, eventually you wrote what is considered the textbook, AI: A Modern Approach. And one thing that I think is important to observe about that is just the foundation that it builds for understanding how AI systems work. And when we talk about AI systems today, kind of in the modern deep learning era, we're more talking about a machine learning algorithm. But if I jump back in time a little bit, look at some of your papers from preceding decades, things like that, there's much more this notion of an agent who is acting and interacting with the world. When you were first getting your start, doing your PhD, writing your thesis, what was the historical perspective at the time? How are people thinking about what AI is? What is it we're trying to create?
Um, so I want to back up a little bit. So we are still working on agents, right? So, and learning has always been the, I think, the primary method by which we expect agents to be constructed. And that goes back to Turing in 1950, at least. Um, and of course, philosophers of science and psychologists all say, yeah, of course, everything comes from our senses and all that stuff. Um, so if I go back to 80, the 1980s when I did my PhD, 82 to 86, um, I would say there wasn't a very clear idea of what is an AI system. Um, this idea of agents was discussed in certain groups, including my advisors group. Mike Genesareth actually wrote a textbook. It's a logic-based textbook, but it puts the idea of agents front and center, and then talks about how you would build a logical agent. And actually, he and I used to build some logical agents. Um, so, but that wasn't widely accepted. The whole expert system era was characterized by the idea that we're sort of building consulting systems that you ask questions of and they give you answers. And um, of course, that's a degenerate type of agent. But if but it's you can kind of ignore the agent status of it altogether. If you say, okay, well, it's supposed to give me correct answers to the questions that I give it. But even then, some people, so for example, Bob Walensky, who was a faculty member at Berkeley, um, was pointing out that even a question answering system actually needs to take an agent stance. In other words, it needs to think about what are its objectives and what are the effects of its actions, where its actions are giving answers to questions. And his favorite example was, if you, the human, say, how do I make more space in my file system? The wrong answer is, well, you just type RM star, right? Even though that's correct, right? But it's unhelpful to the user, and giving that answer will have a bad effect. And other people were thinking about this in terms of medical diagnosis, right? You don't want to give the most likely diagnosis, because often the most likely diagnosis is there's nothing wrong with you, uh, even though you have a 32% chance of brain cancer, and 58%, and so on. So um, it, even if you're building consulting systems, you should think of them as agents. And as I started teaching the AI course at Berkeley, starting in '86, this just became more and more clear that it was the right way to tie together all the work that was going on in AI, whether it was, in natural language. You have to think about uh, a language using entity as an agent, right? And this is something that Wittgenstein and Austin and Searle and various other philosophers had talked about. Speech acts, um, and so on, rather than speech as communicating facts or answering questions. And so, and at that time also in the late '80s, um, Pearl was pushing on probabilistic uh, substrate for AI, and reminding people about decision theory and utility theory and so on, which I'd say wasn't typically taught in any AI course. Uh, and um, and so that really helped, because then you could tie that back to planning, and then you could start to put all the work in AI into a single framework. So that's how that emerged. I think to some extent now, with a lot of these deep learning systems, we've gone back to the sort of AI system as consultant. Where you just you think of it as um, an interface that you could put questions into or images and get back answers. So again, it's the degenerate agent, and almost nobody um, is thinking about it as an agent in the way they should. Um, so the language models are not doing any kind of speech act theory or pragmatics, right? Um, and that's really unfortunate. I think I think that's a mistake. But obviously, the people who are out there wanting to do things in the real world, the self-driving car uh, projects, agricultural robots, et cetera, et cetera. They're all having to think about agents, and uh, what the objectives of the agent should be, and how does it model the external world, and all the rest of it.
That's a very good call out to start with of how the way I kind of phrased in my question to you is not really taking into account, yes, perhaps even the deep learning systems of today, which we might perceive more as utilities, things we consult, an API I plug into in order to feed some text and ask it to answer a question or generate more text.
Right. But I mean, you think about just simple examples, like, you ask it, okay, what's the super user password? Right? Is it going to tell you? I hope not.
Mm-mm.
Right.
Indeed. Yeah, and there's something interesting to think about when it comes to looking at today's language models from that perspective and this whole agenty idea of interacting with the world, which I'd like to get to in a little bit, but maybe staying back with some of these more foundational questions in terms of the foundations of what AI is, what it's supposed to be. Some of your early work looked at the notions of rationality in AI systems. And I believe that some of the, as you were kind of mentioning, some of the ideas that AI took away were grafted over from economics, these theories of people being more or less rational agents. You kind of move that over into this theory of bounded optimality. You also eventually looked at things like meta reasoning. Could you tell me a little bit about what you were thinking about at that time, those particular developments in your own work, what you were responding to?
Um, so again, this was something that was already in the air. Even when I was a grad student, there was a rational agents discussion group um, with people like Michael Bratman and Martha Pollock, and not sure if I remember anybody else, but um, the drawbacks of the perfectly rational agent model, which I mean, to be completely clear, that was in effect the theoretical framework for AI, right? So if you think about whether it's McCarthy or Alan Newell, um, the idea was we're going to build an agent that constructs guaranteed perfect plans and then executes them. And then in areas like game playing where it was painfully obvious that you couldn't actually do that, well, then you just adopted sort of various ad hoc approximations. Like, okay, we won't search all the way to the end of the game tree. We'll only search, a quarter of the way to the end, right? And then that'll do something useful. So you take that model of perfect rationality and you sort of chop bits off until it fits into the machine. Um, and that doesn't give you any kind of theoretical framework because all you're left with is, well, so far my chess program beats your chess program, um, and that's about it. But there's no sense that, okay, this is the right chess program. Um, and so the bounded optimality idea is, how could we replace perfect rationality with something that's actually achievable, but is still sort of theoretically well defined, and in some sense, bounded optimality is trivial. It just says, look, you've got a finite machine. There's only so many programs that could possibly run on it. A large number, but it's a finite number. Um, and some subset of those programs just has better performance than all the others, right? And that's the set that we should be targeting. Those are the bounded optimal programs. And so it makes sense to think of AI as how do we design these bounded optimal programs? And so it has a number of effects on the way you think about the problem. One effect is that you stop thinking about what is the rational action, right? Because in fact, the designer of an AI system doesn't get to control the individual actions. They only get to control the program. And a bounded optimal program in any particular circumstance may take a suboptimal action from the point of view of perfect rationality. But if you tried to fix it so it didn't do that, then by definition it would get worse, right? Because it would start making other suboptimal actions elsewhere, and overall its performance will get worse by definition. Um, so it tells you that to stop trying to think about how an agent should act in any particular circumstance, and that was sort of liberating. And that so we made some progress on um, some compositional theorems, like how could you put together a more complex bounded optimal system out of bounded optimal components that had simpler objectives, and you could chain the objectives together and so on. And so I think um, I think it's still the right approach if what you're thinking about is AI systems that overall have a fixed objective, and we'll get to why that's a bad idea. Um, and it's been revived recently. So, for example, Satinder Singh and Richard Lewis at Michigan, and Josh Tenenbaum and Tom Griffiths, and so these are all computational cognitive scientists, are now talking about bounded optimality as the right theoretical model for understanding cognition and behavior. So that's interesting and reassuring, I guess, that we weren't completely on the wrong track. Um, but it was, probably in the last 8, 9 years, um, I've realized that actually the idea that we're building agents that have fixed objectives is just the wrong. Uh, the wrong way to think about AI.
Hmm. Yeah, we'll definitely get to some of the problems with the standard model in due time. Following up on this bounded optimality idea, and I do remember you had these four stages of rationality that kind of incrementally work their way. I guess the two things that you pointed out there that seem like the high level takeaways here are the contextual framing of my my agent is not something I'm imagining to be rational simpliciter, but it exists within a set of constraints, namely the machine. And B, the other parameter of this bounded optimal agent is, as you said, the program, the thing that a designer can actually intervene on as opposed to individual actions. Where does meta reasoning come into all of this? You had this theory and ideas of how well I can think about the actual computational actions I'm supposed to take as opposed to just existing at the level of doing that computation. And that's certainly something we humans seem to do almost automatically. Could you tell me a little bit about your work there?
Sure. So one of the things I did when I was a grad student was working with Mike Genesareth on his MRS, which actually stood for two different things at different times. But the relevant one is the meta-level reasoning system. So it was a logical reasoning system where the reasoning process was implemented as a set of internal actions. So drawing a particular conclusion, adding a certain fact to the knowledge base, etc. And then you could have a meta-level agent that could direct the object level computations about where the object level computations are the reasoning steps about the world. Like if I drop this glass, it's going to break, and then the uh, the meta level could decide which object level computations to do. And that idea of meta level computation uh, goes back to at least the 1970s. But there was no theory of how the meta level should actually decide anything. Um, so you could try putting in various sort of meta level policies, um, which in some sense, that's what an algorithm is, right? So if you think about, for example, the alpha beta pruning algorithm, which is used for game playing, um, that's a meta level policy that just says, okay, do not do this particular object level computation because it's guaranteed to be a waste of time, right? So do this, but don't do that. Do this, not that, and and that works fairly well. Um, and it just seemed to me that uh, the right way to think about meta level computation was, again, to take this sort of agent view and say, okay, what do computations contribute to the overall goal of the agent, which is to maximize its utility? And in effect, what they contribute is improvement in decision quality. And so you should decide what computations to do based on their uh, expected improvement in decision quality. And I was still interested in game playing, and that was a good example where the object level computations are fairly simple, right? They all just expand a leaf node of a tree and add the successor states to the tree, and then evaluate the successor states, and then back up the values in the tree. And so the question would be, well, which leaf node should I expand? And so instead of a sort of complicated algorithm like alpha beta pruning and innumerable variants and hacks and improvements on that, I just said, okay, we should just expand the leaf node such that we expect our decision quality to improve the most. And that's it, right? And then all you have to do is figure out, how do you quickly compute the expected improvement in decision quality that results from expanding a leaf node. So when you expand a leaf node, what could happen is the value of that node by looking at the successes, could increase or decrease, right? And you don't expect it to go one way or the other, but you expect it to change. Um, and then you can sort of follow that back to the root and say, well, look, even if we change this leaf node by plus or minus 50, because there's an alternative route you could take from the root, alternative path, it's actually not going to change your mind, right? So if there's no possibility that you're going to change your decision at the root, then there's no value to doing this computation.
Right.
And alpha beta pruning is just a special case of that assumption, actually. Whereas this more general way of thinking will tell isn't just saying, well, the value of expanding that leaf node is either 0 or non-zero, right? It actually gives you a quantitative estimate, which allows you to rank which ones you should expand first. So you get typically a much deeper search tree along certain branches that are interesting and important to pursue, and then other branches where, for example, the move is obviously bad, it'll just stop doing anything, right? And won't even bother thinking about it because it's so clearly bad that there's no point in finding out exactly how bad it is. And so you get search trees that are much narrower, much deeper. And we showed that relative to alpha beta, at least up to a point, you got much more efficient search. I think we maybe about 60 times more efficient in some of our experiments. And this approach, the same algorithm, can play backgammon, can do, single agent, like finding routes through a complicated obstacle course and all sorts of stuff, right? And I think that was a really important higher level point, is that if you think about how a general intelligence system is going to work, when a new type of decision problem comes along, so let's say you go from ordinary two-player games to two-player games that include a dice, so you have chance nodes, right? You can't hire a PhD student to come along and invent a new algorithm and stick it into your head, right? You got to have one mechanism for managing all the computational processes uh, in your brain. And so this is a good candidate that you have meta reasoning, so general meta reasoning capability that works no matter what the nature of the underlying decision problem is. And we could even speculate about how the brain might implement that using, spreading activation or something. I don't know exactly what, but so it's a very rich area, and there are implications for cognitive sciences. So one of the things we noticed was that suppose you have significant uncertainty about the value of two different actions, but that whatever the values are, they're essentially the same, right? Because of, let's say, symmetry. And we noticed introspectively that humans have a hard time just sort of mentally tossing a coin and saying, you know what, it doesn't matter, right? I can't figure out which of these two is best, so I should just stop thinking about it and get on and just do one of those things. And then, many years later, a grad student of Tom Griffiths, folk leader, started working on the question of, could you train humans to actually do a better job of their own meta-level control in that particular circumstance. So it anyway, so that's meta reasoning, and how does it fit in with bounded optimality is an interesting question. So I think you shouldn't think of meta reasoning as the solution to what a bounded optimal program should look like.
Sure.
Because under some circumstances, meta reasoning is an expensive luxury, and you should just you just have to react, right? I mean, when you blink, if a fly flies towards your eye and your eye blinks, right, there's no meta reasoning going on, right? It's not saying, is it a good idea to blink? And okay, let me think about that. Right?
Right.
It just blinks because you need to blink. And that's why it's really hard to put eye drops in, right? Because you stick this thing towards your eye, and your eye says, "Okay, I'm blinking, right? I'm going to close my eye," even though you don't want to close your eye. It still happens. So the way to think about it is that it's one possible agent architecture, and within that class of agent architectures, you could try to optimize the amount of meta reasoning that happens, or how it's implemented, because you can't do meta reasoning exactly, right? I can't say, okay, what is the best computation that I should do next? And the reason you can't do that is because computation itself is a sequential decision problem. So let's say you're playing chess, which is a sequential decision problem where you're going to make 100 moves, right? But the computational problem of deciding what chess move to make, right? You might, as Stockfish does, you might do 1 billion computations, right? And then which 1 billion computations you should do in which order, right? That's way harder than playing chess, right? A much bigger state space, right? The state space is not the set of all board configurations, it's the set of all trees, where each tree has possibly millions or billions of leaves, and each of those is a board configuration. So you've got a vastly bigger state space and vastly longer solution sequences. And so there's no chance that you could actually have optimal meta reasoning. And I think that was something. So various other authors like I.J. Good had thought about something like bounded optimality, but they sort of got stuck on this idea that, oh well, we should compute optimally, and you can't, right? Because that creates a meta level problem that's even more intractable to solve, and so you can't compute optimally. But you can have, for example, an adaptive process which over time adjusts its computational behavior to the environment and to the amount of resources that it has, so that it is approximately bounded optimal. And so that's something that I think people are pursuing now.
There's certainly a lot in there. And I guess there are certainly some natural analogs that you pointed out along the way in your answer of how we humans do our own little meta reasoning. So when I'm thinking about playing a game of chess, you also mentioned backgammon as a concrete application. Just the idea that, well, in my head, I'm thinking about possible moves to explore, possible responses my opponent might make. And I might think of one and be like, well, it would be incredibly stupid for my opponent to do that. And so it's just not really worth expanding that tree further, as it were. And
Yeah, I was going to say, I mean, this applies to daily life,
mhm,
right? And it's just remarkable. I mean, sometimes we do daydream, right? Which sort of means thinking about stuff that isn't relevant to the actual problems we face. But and this is an area I think that's potentially very exciting. Our our thinking about our lives and the decisions we make all the time is clearly hierarchical, right? That we say, oh yeah, today I'm going to do the podcast interview, right? And so I better get out of bed and so on. And then once you're in the podcast interview, then you think about what to say, and so on. But then at the same time you're thinking about, okay, what am I doing this week? And okay, I'm going to England for Christmas. And okay, when am I going to start writing my next book? So on. So all the way down to the control signals that your brain is sending to your fingers as you type, or to your vocal apparatus as you speak. So you're thinking and controlling the computational processes across many levels of abstraction in many different orders of magnitude of scale, and somehow it all just works seamlessly, and that's very powerful. So because when you think at a higher level of abstraction. So I think a good example would be like taking a vacation, right? Well, so if you think about a week-long vacation in terms of motor control signals, right? It's billions of motor control signals. So if I started to say, okay, well, should I, move my left foot first or my right foot first when I go on vacation, right? No, you say, where am I going to go on vacation, right? Should I stay home? Should I go to Hawaii? Should I go to Tahiti, right?
Mm-hmm.
And that one high-level decision has a huge impact on the utility of your vacation. Okay, so because we can think at these higher levels of abstraction, that makes available computations that have extremely high value, right? Whereas if we could only think at the ground level of, well, should I move my left foot or my right foot, right? Almost all computations would be useless because
Mm-hmm.
they don't add any value.
Right. There's a sort of simplification or abstraction that occurs when we think about what actual concrete explicit thoughts and activities we attend to, and there is something really fascinating about it, the way that we have these very intuitive notions of things being in space and time, for example, to the point where I don't have to think at such a granular level about what it means to take my pencil and put it over on the desk, for example. There's so much involved in that, not just my my motor system, but also where exactly is the desk and all of that. I just sort of perceive the thing, it's there. I have my object, the pencil, and I'm putting it on the desk. And there's not much that I think about at a more granular level.
Right. Well, your brain is doing it, right? So your brain has to spit out tens of thousands of motor control commands in
Right.
order for you to just move the pencil to the desk. And um, so I think was Whitehead, as in Russell and Whitehead, who said civilization advances by reducing complex operations to the trivial, or something was to that effect. And I think that's a good description of what's going on here.
Hmm. I think this is perhaps a good segue into the next section of time. So we've been discussing how our brains, while they do have to give millions of instructions, the explicit thoughts that exist in our head can more or less be at higher levels of abstraction. And one one criticism of the recent years we've been seeing in terms of deep learning, we can look at, for example, the consciousness prior ideas of how do we bring higher levels of abstraction to today's learning systems. Is that when I look at a convolutional neural network, for example, it is operating very much in the kind of ground level pixel space, which does make it possible for today's deep neural networks to pick up on spurious patterns because they're thinking more at the level of what are the different pixels in this image. And this sort of divide we're seeing here, there's a lot of seeds that came a lot before. There were the connectionist and symbolic camps in terms of looking at how AI was to be done. And you yourself have said multiple times that deep learning itself is going to hit a wall and perhaps we'll see a shift back towards a more explicitly agent focused perspective on AI, as we've been talking about. Could you tell me just about how this recent rise in deep learning has struck you as a researcher and what you think about how some of those connectionist symbolic debates are really playing out today?
So it's a very interesting question. So I should probably back up a bit and talk about some of the work I did from sort of mid '90s to mid 2000s, um, and uh, and that's basically trying to increase the expressive power of probabilistic modeling languages. Um, so so when Udaperl dragged the AI community kicking and screaming into the probabilistic era, um, you know, he proposed base nets, which, well, I don't know if he, there were several people who had similar kinds of ideas, but I think he was the main apostle of Bayes nets. So Bayes nets are, very roughly speaking, the probabilistic generalization of Boolean circuits. And nobody actually thinks the Boolean circuits are a good substrate for anything really, except for very, very low level kinds of signal processing or basic operations in a computer. Right? No one writes payroll systems using Boolean circuits. Right? We use programming languages, and in AI, over the first few decades, we said, okay, we want to have systems that know things and reason and plan with that knowledge and learn that knowledge from experience or from other people, through language and so on. So this concept of a knowledge-based system is in some ways the central uh, contribution, key idea of classical AI. And so in order for that to work, it has to be expressive, right? The language has to be expressive enough so that the stuff you need to know, you can know it in a reasonable form, right? And to give you an example, right, if I need to know the rules of chess, right, in first order logic, I can write the rules of chess in about a page. Same for Go, right? In circuits, it's hundreds of thousands or millions of pages. So it's just a complete non-starter as a hypothesis about how we know things, right? That we know them by having giant circuits that implement the appropriate function, right? It's just
Right.
a complete non-starter. Um, and so what I was trying to do in the 90s, with people like Daphne Koller and others, and Joe Halpern, Cornell was working on this, and Fahim Backus at Toronto, was um, how do we get the expressive power that we have in first order logic, right, which lets us write things like the rules of chess very concisely. In fact, a whole bunch of common sense knowledge is easy to write down in first order logic. How do we combine that with probability theory so that we get the ability to handle real uncertain information from sensor data, uncertainty about the physics of the world, and so on and so forth. So we developed uh, various approaches. So Daphne and another undergrad student in my group, Avi Pfeffer, and David McAllister wrote the first probabilistic programming paper in '97. And their view was, yeah, we'll combine ordinary programming languages with probability theory and get the expressive power that way. I wanted a declarative language, so I wanted a combination of probability theory with first order logic, which I developed with Brian Milch and Hannah Prasula and a couple of other students. David Sontag, who's now at MIT, was another one. And so that became Blog, or the Bayesian logic language. And from there, eventually, now probabilistic programming is a fairly big field, with a couple of thousand papers a year being published. And um, we built some quite significant systems like the monitoring global monitoring system for the nuclear test ban treaty is one example. So that's running 24/7 in Vienna, detecting all the seismic events on the planet and classifying them. Um, so when I see deep learning, which is just based on circuits, I say, well, you're missing a basic point about expressive power. Um, and so, uh, you know, so what would you expect as a result? You would expect that it requires, enormous quantities of training data, because, if you don't, for example, if you think about the rules of chess, right? all 8 of the pawns move the same way. But you've got no way of expressing all the pawns in a circuit, right? You have to, in some sense, write a circuit for each of the pawns somehow. And then for each of the squares it can be on, right? You can't say, well, everywhere between row 2 and row 7 it behaves the same way, or sorry, row 3 and 7 it behaves the same way in all the columns, right? So you've got to rewrite those rules for every square. I mean, if you're really insisting on just circuits, you've got to rewrite it for every time step, and so on. So you need, in order to fill in all that stuff, you need billions of training data, training examples, and that's exactly what we see, right? That in some sense you're almost creating a lookup table rather than a simple generalized representation of the rules of chess, and so that's the sense in which I think they're going to hit a wall. And you could sort of take an even more like non-technical common sense approach to this. It's as if I was to say, okay, here's how, I go back to the late 19th century, and we want to create an engine that will drive cars, right? So here's how we're going to, we'll call it the internal combustion engine for reasons we don't yet know, and here's how we're going to do it. We're going to take a big block of steel and we're going to run gradient descent, right? And it's going to invent the internal combustion engine. Like, well, no, it's not, right? I mean, we did that in the 50s. People said, oh yeah, we're going to create AI. Here's how we're going to do it. We're going to take Fortran programs and run evolutionary operations on them. We're going to do crossover and mutation, and that will produce AI. Right? I mean, theoretically, yeah, it's possible, but it's just like saying, yeah, theoretically, it's possible for all the oxygen atoms in your room to move over to one side and for you to die of asphyxiation, right? Yeah, theoretically, that's possible, but it's astronomically unlikely. And it's just not a plausible approach to the technology. So having said that, what's impressive about the deep learning systems, which I guess we should have thought about. I mean, maybe we did think about it a long time ago, but if you think about all the people working on machine learning who weren't doing deep learning systems, right? So people doing decision trees, people doing linear regression, logistic regression, all that kind of thing, right? Decision trees give you sort of long and narrow. Linear regression gives you wide and shallow, right? But nothing gives you both wide and deep, right?
Right.
So, but complicated functions, especially from high dimensional inputs, have to be wide and deep. So you need some sort of hypothesis space that's wide and deep, and so that's at a very high level what happened. And once you have that, now you've got a new toy, right? Which can do a lot of interesting things. I think the deep learning community has been extremely creative at finding ways to use that new toy, right? I mean, things like style transfer. Here, take this photograph and re-render it as a Renoir, right? It's sort of really interesting, and people are constantly dreaming up new ways to use this toy. But on the other hand, problems to which it's just not applicable at all. Like, okay, we need to build billions of batteries for electric vehicles, so we need to design a gigafactory. Okay, great. Well, in AI, right, that was something that people worked on in the 70s, right? Literally designing factories from the ground up. Um, and all the way through to the actual construction plan for building it. But if you said that to a deep learning person, their mouth would just drop open, and then they would sort of go back. Yeah, but we're really good at looking at images, right? I mean, and so a vast range of problems that are interesting and important are simply, airbrushed out of existence, because there's absolutely nothing that deep learning can contribute to them. Um, so I think the right answer is not that the pendulum swings back and we stop doing deep learning. We go back and just pursue all the same routes that we were pursuing before. Um, I think the answer is that the which is how it always happens, right? The deep learning people um, start adopting some of the ideas of classical AI about how you decompose an agent into different subparts and how those subparts communicate with each other. And then they'll just say, well, we're still just doing deep learning. And then the more classically trained people will say, yeah, we'll find ways to put deep learning into various of the component interfaces and the perceptual part and so on and so forth, and say, yeah, we're still doing classical AI. They'll end up with, in some sense, identical systems, but they'll just think about them in different ways. So if you look at Waymo, for example. So actually, the whole self-driving car area is really interesting, and some of it's proprietary. So I don't know everything that's been going on, but for sure there were groups that said, okay, we'll just do end-to-end deep learning. That's how we're going to build our agent. So it's still an agent. It's still taking percept sequences and generating actions. But just like the big block of steel in the internal combustion engine, we're just going to make a big block of circuit, and we're going to train it end to end to be a good driver. And I don't think that worked at all. I mean, I remember having this discussion with the Uber guys when they were just starting out. I said, look, if you take that approach, you're just going to kill people. And that's what they did. So, and then they stopped. So, and what Waymo did initially was actually even more old-fashioned AI than I would have recommended. Right?
Hmm.
So they had a perceptual layer that was based on trained deep learning recognizers for pedestrians and road signs and where you are on the road relative to the markings and so on, and the other vehicles. And then they output from that essentially logical assertions, right? So it was actually pretty similar to the shaky robot from 1971 at SRI, right? So it outputs sort of logical assertions, right? There is a pedestrian at 17, 13, 8, right? And there's another car, and here's the bounding box, and this is right. So definite logical assertions. And then they had rules, logical rules of the 1970s, what we call production system, which is basically a set of if-then rules where the if part is could be an arbitrarily complex logical expression, and then the then part is whatever action the system should take. So if I'm in the middle lane and there's a car to the left and a pedestrian to the right and the traffic light is yellow and blah blah blah, then stop. And
Hmm.
they ran out of rules all the time. So they would find, every day. So Astro Teller, who used to run Google X back when this is part of Google X, um, said that the engineers would come back at the end of the day and said, oh, well, we came to a traffic circle and there was a little girl riding her tricycle the wrong way around the traffic circle, and we didn't have a rule for that. So the car didn't know what to do, right? And the next day will be another story, and the next day will be another story, and then they realized that you can't ever write a set of rules that covers all circumstances. Well, no big surprise there, right? Same problem in chess. You can't write a bunch of rules saying what move to make that will cover all the possible board states that you could ever get into in a game, right? How do we do it instead? You go back to first principles. You say, well, here are the actions I could take, and here's how the world would respond, and here's what I would do then, and here's what I would do then, here's what I would do then. You look forward through action sequences from you and from the world, and then you choose the best one. You can do that with driving as well, as long as you see now you need two things. You need models, because you can't predict forward without models. You need to keep track of other behaviors and model intent of the other drivers and so on. And you need an evaluation function. right? You can't just say do this. You have to be able to compare the desirabilities of different courses of action. And so then you're very much back in the classical AI way of thinking, a model-based, look-ahead, deliberative system with an evaluation function. It's just a little more difficult because it's probabilistic and continuous,
Hmm.
and so on.
Yeah.
And the objective is less clear.
Very true. I think this will be a good segue, but if I can just comment a moment on some of what you were saying, I do share some of your intuitions about the limitations you expressed about deep learning, and I share that intuition that there's a lot of what's going on that very much feels like a lookup table, but at the same time, it's I guess just worth mentioning there does seem to be something kind of fascinating and nuanced occurring in these networks, especially when trained at scale, that I think has been coming up in some of the foundational work that's been done on deep learning recently. So, if we look at, for example, Christopher Manning's work, looking at how they found these universal grammatical relations in multilingual BERT, yes, the sample efficiency is pretty bad, but after the massive scale pre training it's undergone, it is able to pick up on things that look like aspects of universal grammatical relations, things that kind of came out of Chomsky, and it's able to, for example, distinguish between pre-nominal and post-nominal adjectives, which is pretty interesting. And so I do agree with you that there are definitely significant limitations, but it does feel like when they do get trained to scale, yes, sample efficiency is pretty bad. Yes, there's a lot of lookup table memorization stuff occurring, but there is something really interesting there. And certainly we don't understand all of it, which is a problem in its own right that also deserves a lot of work. But
Mm.
there's definitely something nuanced and interesting going on in there, I think.
Yeah, I think that um, in many cases you can get effective generalization sort of without going all the way to the full expressive power of programming languages or first order logic. And um, if you said to somebody, okay, write a PCFG parser, so probabilistic context free grammar parser, they could do that in a programming language, right? They could do that in Python. It's like 75 lines of Python or something. It's not a huge problem.
Right.
And if I said to them, okay, do it with a circuit instead, they would be lost, right? But one solution is, oh well, okay, then implement a Python interpreter using the circuit, and then write 70 to 75 lines of Python. Right? That's probably unnecessary, right? There are ways of getting the degree of generalization that PCFGs support using circuit implementations. We just don't know how to do it.
Hmm.
And so it's possible that that the deep learning circuits are actually figuring out those sort of ingenious circuit designs that give you some of the same types of generalization. For example, that there are ways of thinking about the vector space representation of words as essentially sort of a symbol lookup table. And having a symbol lookup table that's one of the key components of an interpreter for a programming language, if you think about it. So, uh, so I think that's interesting. I just think it's a weird way to go about it, right? Because we've done decades and decades of deep mathematical research trying to understand logic, well, thousands of years on logic, decades of work on programming languages and so on, and throwing it all away doesn't seem like a good strategy. The other thing that I find interesting and again potentially exciting is the difference between what seems to be happening in just object recognition deep learning. So you make your 80-layer ResNet and you train it on ImageNet data, and it's not at all clear that it's actually recognizing the objects in any sense. And there's some evidence that actually it's often not even looking at the object at all, right? It's just learned that that particular type of dog always sits on this particular color of carpet. And so it just finds that color carpet and says, okay, then it's definitely a Norwich Terrier,
Right.
right? Without even looking at the dog at all. And similarly, if there's enough blue sky in the right places, then it must be a parachute. Or in the case of CFAR 10, right? If this one pixel is gray, it's definitely an aircraft, right? Literally one pixel is all it uses to make that classification. So, whereas if you look at what's happening with the text and image models, right? It seems pretty clear that they're in some sense parsing the images correctly because they're able to reassemble components of those images into new images in the right way. So they're clearly, if it's the panda, right? What was it? That was I just saw the Chinese one, handsome panda riding a motorcycle. It's not a brilliant image, but clearly it's pulled the panda out of the panda images. It's pulled the motorcycle out of the motorcycle images. It's put them together in the right way with the right occlusion, and so it's clear that there is approximately the right type of analysis of the image going on. Why? Again, we don't know.
Sure.
But that's sort of interesting and exciting. And I just wish we had better forensic methods of understanding how they work.
Yeah, yeah. It does seem like there's a lot of good work going on that front. I know Chris Ola's work at Anthropic, for instance, has been looking at mechanistic interpretability. I realize we're very much running up against time here. Maybe just for a very quick 2 minute thing, because I want to make sure we have time to talk about your current research agenda a little bit. You wrote this wonderful book, Human Compatible Artificial Intelligence and the Problem of Control. And we've been pointing at this a little bit earlier, but you have found problems with the standard model of AI in that an agent knows what its objective is, chases after it. And there's certainly a lot of debate on this front between people who, like you, are looking at the long term problem of superintelligence, general intelligence, and what risks it could pose, and others who are more like, well, we need to be thinking about short term problems, and these long term problems are more or less a waste of time. You do respond to a lot of the kind of common objections in your book. So perhaps just as a short take on this, could you maybe steelman that side, give me what you think is the strongest argument against the long-termist perspective, and maybe a quick summary of why you think it's so important to be thinking about these problems right now.
Honestly, I don't think there are any strong arguments against the long term perspective. So let me be completely clear. It's this idea that it's sort of either or, right? Either you work on short term problems or you work on long term problems, and there isn't enough brain power in the world to do both, right? I mean, this is just ridiculous. Like saying, well, climate is really important, so we should stop working on criminal justice,
Hmm.
right? I mean, it's a bonkers form of argument. Climate is important, but I'm not a climate scientist, so I work on AI, and I think, you know, the the characteristics of the long-term problem in AI are in some sense worse than for climate, right? In climate, the vast majority of the world understands that there is a major problem, but we just, there's a small subset, the fossil fuel industry, that's very influential and keeps pushing us to not solve the problem and so on. Whereas in AI, right, the vast majority of the field is just focused on how do we create more and more capable AI systems. And I began back in the first edition of the textbook saying, "What if we succeed?" Um, and I think to those who say it's not worth thinking about, I would say, well, then why are we investing hundreds of billions of dollars and hundreds of thousands of people's lives and minds into something where if we actually succeed in it, the outcome could be arbitrarily bad for the human race, right? So what, I could sort of just put the question back on them. So what's your plan for when we succeed? How do you propose to control systems that are far more powerful than human beings forever, right? Uh, and so um, that's why I think it's important for at least some people to put a lot of thought into this. Um, and so the thought that I put into this so far, I tend to agree with various others like Bostrom and Yudkowsky and so on, with and Steve Omohundro with his basic AI drives paper and so on, that um, the core of the problem is misalignment, right? The idea that if we design AI systems that have fixed objectives that are assumed to be correct, and they pursue them with greater and greater intelligence, um, almost certainly, and certainly in all cases so far, those objectives are not complete and correct representations of the preferences of the human race for its own future. And so when you have misalignment, the outcome is arbitrarily bad. And and so what I realized back in, I guess, 2013 was, okay, you need AI systems that know that they don't know what the objective is, and that's the only way forward. Or you could think of it the other way, right? In some sense, they know that the objective is, the furtherance of human preferences about the future, but they don't know what those preferences are, and that creates a whole new class of problems. And in some sense, it's a strict generalization of everything we've done so far, right? Everything we've done so far assumes that the objective is exactly known, right? And just as happened in the 80s when we sort of finally accepted uncertainty, uncertainty in the state, uncertainty about the transition model, right? There's uncertainty about the objective. And that particular type of uncertainty is really interesting and has different technical consequences from other types of uncertainty. Um, but it's still something that we can make progress on. We can still design algorithms that behave rationally when they don't know what the objective is. And roughly speaking, right, they have an incentive to learn more about the objective. They have an incentive to behave carefully so they don't mess up parts of the world that they're not sure you want messed up in that particular way. They have an incentive uh, to be sort of deferential to humans because the human commands or prohibitions are expressions of preference that presumably the machine was previously unaware of, and so it's natural that they would defer to those. Um, and we showed that, in the extreme case, uh, machines designed this way will want to be switched off if that's what humans want to do. And so there's still a long way to go, but it seems like qualitatively this step um, may be the core of the answer to the control problem in the long term, and opens up huge new areas of basic AI research to make it work. And if all goes well, there's an NSF program in the works, and if that comes to fruition, there'll be a big NSF-funded research program next year
Mm-hmm.
to make this happen.
Absolutely. Well, I wish we had more time to go into all of the gory details of this, but I do think this was a really good summary, and there are plenty of other places where I think our listeners can learn more about the particular problems you're solving. So perhaps to wrap up, Professor Russell, I do want to say, first of all, thank you for everything you've done to bring just the basics of AI to so many people, as well as your current work trying to explain the problem of control to so many people. It was really an honor speaking to you today.
It's a pleasure. Thanks a lot.
And that is a wrap, my friends. As I mentioned at the start of the episode, you can subscribe to The Gradient on Substack to receive not just this podcast, but also our articles and newsletters directly to your email. You can also visit us at thegradient.pub, where you'll find all of that, as well as more information about The Gradient and how you could even contribute if you're interested. And finally, if you enjoyed this episode, we would really appreciate your feedback. If you'd like to leave a comment or review, we'd love to know how we can make this series more interesting and informative to you. And with all that, I'll leave you until the next episode.